Mr. Giroux, in this lesson we are going to be looking at some basic properties of real numbers, associative and commutative property of multiplication and division, or excuse me, addition and multiplication. Division doesn't have associative properties, as we'll talk about, or commutative properties for that matter. We'll be looking at identity properties of addition and multiplication. What can you add or multiply by and still get the same answer? Zero product property. What happens when you multiply by -1? We're going to simplify some Algebra 1 type expressions, and then finish off our video talking about counterexamples. In other words, how can we prove a statement is false by simply using a counterexample, and how does that compare with deductive reasoning, which is kind of basically how we prove that two algebraic expressions are equal by walking through these properties we're going to learn to show how one expression is equal to another, usually another expression in simplified terms. A relationship or relationships that are always true for real numbers are called properties. The key word here is always true. For something to be true in mathematics, it must be true an infinite number of times, like 10 million, 10 billion times, and never fail. If you can come up with one counterexample, like we'll talk about at the end of the video, even if it fails one time out of just an uncountable number of successes, then it is a false statement. So we use these properties to rewrite and compare expressions. That comparison of expressions is what I'm talking about with our deductive reasoning. So equivalent expressions are two algebraic expressions that are equal for all values of the variables. So if you have, we'll come up with some examples later, but basically I'll give you an algebraic example, or two of them, and regardless of what number you plug into, or numbers that you plug into those two expressions, you will get the same numerical answer. Those are equivalent expressions. Properties of real numbers. Well, we're going to let A, B, and C be any real number, and we have the commutative properties of addition, which says that we have A plus B is equal to B plus A. In other words, we can change the order of the addition and still get equivalent expressions or equal answers. And then we have the multiplication, which is A times B is equal to B times A. So again, we can turn that order around, move the numbers. Like if I want to commute to work, I move from where I'm here at home, to work. I drive to work. So commuting is taking these values and moving them around and basically just switching places in these expressions or equations as it may be. So here we have some examples of statements that are true, and we're going to actually validate whether or not they're true or not, do a little bit of arithmetic. So we have 3 plus 5, which is equal to 8. And we have 5 plus 3, which is equal to 8. And hopefully we, just know that from, obviously earlier years of learning math. But when you add on a number line, you move to the right, and when you subtract, you move to the left. Or when you're adding negative numbers, you move to the left. So from 0, we move right 3, and then right 5 more times. That's of course going to give us an answer of 8. We start from 0 and move to the right 5, and then 3 more steps to the right because of the addition of these positive numbers. We get 8 again, and of course that's a true statement. That is an example of the commutative property of addition. I've taken these numbers, I've moved them around the addition sign, and I get equivalent answers. Now here I've got some negative numbers going on, and hopefully we're a little bit comfortable with positive and negative numbers, combining them. If not, we will be talking about that in the next section of our next lesson for algebra, where we have 2 plus -3. And you can think about positive and negative numbers a couple of ways. You can talk about money, like as a positive number is money coming in, and negative numbers are money coming out or going out. So if we have positive $2 and we want to spend 3, we're going to be short or owe $1, giving you an answer of -1. Now another way of thinking about that is again with the number line. And if you have 0 here, and we move 2 places to the right, because that's a positive 2, so 1, 2, and then we're adding a -3. Well, we've moved 2 spaces to the right, and that -3 is going to move us backwards. So I'm going to move back 1, back again, and that's -2. We're back to 0, and back to the left one more time for the -3, stepping 3 spaces to the left on the number line. Again, from 0, positive 2, 2 right, -3, 3 to the left, and we're at -1, 1 space to the left of 0, and again that's how we get that -1. Well, You got to be careful with this example here, which I'm including purposely, even though I'm going to talk about combining positive and negative numbers in the next section, because there is no commutative property with subtraction, but I'm taking the negative that's in front of the 3 and I'm moving it with the 3. So here I have positive 2 plus a negative 3, and I've moved those numbers around the addition sign and put the negative 3, I've moved the negative with the 3, and kept it out front. So now we have negative 3 plus 2. Well, that is also going to be negative 1, and we have a true statement. So there's 2 examples here of the commutative property. And just one more time, if my hand is 0, we have 3 movements to the left and 2 movements to the right. So if we're here, we go 1, 2, 3, and then back 2 is still going to land us 1 space to the left of 0, or put us at negative 1. Well, here, see, I made these very close on purpose. I have 2 plus negative 3, and that is actually an equivalent statement to simply 2 minus 3. Again, 2 movements to the right, 3 movements to the left, or if you want to have, if you have $2 but you want to spend 3, you're going to owe somebody or be short $1. And if I come over here to the other side, you notice how I took those numbers and I changed their places, but here the 3 has a minus in front of it, or a negative sign. And over here, the 3 is positive. So I've just taken the positive 2 and the 3, ignoring the minus sign, and I've changed their places, and I've tried to show what would look like the commutative property of subtraction. Well, positive 3 minus 2, I mean, if you have $3 and you want to spend 2, you'll still have 1 left over, and negative 1 is not equal to positive 1, and this is an example of why, a counterexample of why we don't have the commutative property of subtraction. Or again, with your number line, if there's a 0 here, there's positive 3 to the right, 3 steps to the right. Our negative 2 is going to back us up 2, and we're 1 space to the right of 0, as opposed to before we were 1 space to the left. Multiplication, 4 times 5 is equal to 20, and 5 times 4 is also equal to 20. So again, we have that commutative property of multiplication going on here. And 1/3 of 15. Well, 1/3 of 15, when you start working with fractions, you really should just make everything look like a fraction, so that you can see, and there's a couple ways you can simplify this, but 1 times 15 is equal to 15, over 3 times 1, which is equal to 3. And on the right side, we have, if we place that 15 over 1, to make sure we see that our numerators and denominators are lining up. And you'll notice I'm not going through the process of finding common denominators, because you don't need those when multiplying. So we have 15 times 1 is 15, over 1 times 3, which is equal to 3. And we have an equivalent statement here, which is, that 15 over 3 is equal to 15 over 3. Now really, I kind of prefer you and my students to write 15 divided by 3 is equal to 5. So really, as a simplified form, this really should say 5 is equal to 5. I showed us a counterexample for subtraction, showing you that you cannot just change the order or use the commutative property with subtraction. The same is going to be true with division. There is no commutative property with division. So if I clean this off real quick, and let's say we have 20 divided by 4. Well, that is the same as 20 divided by 4, which that, either way you look at it, is equal to 5. If I try and change this order around and write 4 divided by 20, that's going to be 4 divided by 20. Well, now this time, that doesn't equal 5 again, because it's the top number divided by the bottom, and 20 doesn't even go into 4 once, much less 5 times. Now, 4 and 20 are both divisible by 4, so I can reduce the fraction, dividing the numerator and the denominator by 4, and get in an answer of 1/5. So again, we do not have a commutative property of subtraction. We do not have a commutative property of division. I just gave you a counterexample for the division. The associative property of addition and multiplication, well, that says, now associative, to associate with people, is to group with them, to make friends, basically. So the associative property of addition and multiplication is about regrouping the numbers, not moving them like we do with the commutative property. So our example here says that we have a plus b in parentheses plus C is equal to A plus B plus C. And we basically have a very similar statement for multiplication. Well, if you remember your order of operations we just spoke of recently, or you learned in your math class, you have to work inside the parentheses first. So when I see 7 plus 2 plus 1, those parentheses are telling me that I need to add the 7 and 2 first. So we get 9 plus 1. And over here we have 2 plus 1, which is 3. And 9 plus 1 is equal to 10. Excuse me. And 7 plus 3 is also equal to 10. And we have equivalent statements. So we were allowed to move the grouping symbols, if you will, in this example, and get equivalent statements. It's at least one example. It's not a proof, but it is at least one example of the associative property working. Now, why don't we have associative property of subtraction? Well, if I come back up here, and let's change this negative between the plus sign between the 7 and the 2 into a negative sign. Actually, let's just highlight that in a different color so you know that I've changed the problem. 7 minus 2, working inside parentheses first, is 5. And, well, we got to work in these parentheses first now with the, trying to apply the associative property to an expression that includes subtraction. And we have 2 plus 1, which is 3. Well, 5 plus 1 is 6. 7 minus 3 is equal to 4. And that, of course, is not true. So again, we have an associative property of addition, like my original example, right before I changed it, which worked. I included a little bit of subtraction in there. Now, the associative property fails. That counterexample shows that we do not have an associative property of subtraction. And it works with multiplication. I'm not going to do a counterexample for this, but we have 4 times 2 is 8. We have, working in parentheses first, 2 times 5 is 10. And 8 times 5 is 40. And 4 times 10 is 40 as well. If you're just getting into algebra, this is basically my 3rd or 4th lesson, I believe, in my Algebra 1 course. So you might be tempted still to use a little cross for multiplication. Well, of course, in algebra we're working with variables, and a lot of times those variables are x's. So an x, a variable x, a letter x, looks exactly like a multiplication symbol of x. So we avoid those at all costs. Don't ever use just an x for multiplication in algebra. You're going to get confused with that multiplication symbol, and sometimes when it's actually a variable. So use the little dots or parentheses to indicate multiplication, not x's. Next screen. Identity property of addition and multiplication. Addition. If you add by 0, nothing changes. So that any number plus 0 is equal to any number. If I don't know if I got $4 in my pocket and you give me absolutely nothing and I spend nothing, I still have $4. Okay, multiplication. Any number times 1 is equal to itself. So 5 times 1 is 5. I actually could put a number up here. How about 7 plus 0 is still equal to 7? We have 7 times 1 is still equal to 7. Any number times 1 is equal to itself. And by the way, when you're setting up algebra, like adding like terms, or even multiplying if you will, but especially adding and subtracting like terms, it's a really good idea actually if you're giving a variable and there's no number out in front of it. Might be a little much for these rules, but you know, like if you do a plus 5a and you keep forgetting to say that it's 6a because 1 plus 5 is equal to 6, then go ahead and remind yourself by literally writing that 1 in there, that coefficient of 1 in front of your variable. Okay, so, but these identities are unique to that particular math operation. If I multiply by, if I add by 0, nothing happens, like 7 plus 0 is still 7, but if I were to multiply by 0, a lot happens. Anything times 0, the product of any number and 0 is 0 itself. And this comes in very, very handy. It kind of seems like it's obvious. Like, well, yeah, I know that, 3 times 0 is equal to 0. You don't have to tell me that. I've been doing arithmetic and using that for years now, maybe, in your math history. But this idea in algebra that anything multiplied by 0 is equal to 0 is extremely important, because later on in this year, and you'll review it in geometry, and you'll review it again in algebra 2, and so on and so on, you're going to learn something called factoring. You're going to solve equations by factoring them, and this product, or this zero property of multiplication comes in very handy and is very, very important. So a times 0 is equal to 0. Anything times 0 is equal to 0. And when you multiply a number by -1, well, when you multiply by 1, you get the exact same answer back. But when you multiply by -1, that negative sign is going to change the sign. So any number multiplied by -1, any number multiplied by -1 is going to be that same number, because we multiplied by 1, which is the multiplication, this is the identity for multiplication, but that negative is going to change the sign. So if we have 5 times -1, that's going to be equal to -5. Yes. Or if it was initially -5 and I multiply by -1, well, we know that negative times negative is positive, and we get a positive 5. So maybe we want to think of multiplying by -1 doesn't give us a negative answer, but actually changes the sign. Okay? So because A, this idea of A can be any number. It doesn't have to be just a positive number. So -5 times -1 is positive 5. So when you take any number and multiply it by -1, you actually get the opposite answer. You shouldn't really say this, and I think I just did, so I'm going to correct myself now. You shouldn't think of this as -A, but the opposite of A. So any number times -1 gives you, or equals, the opposite of what you originally started with. So -5 times -1 is positive 5, because 5 is the opposite of -5. And by the way, with opposites, you know that two numbers are opposites when you add them and you get 0. Any two numbers added together that gives you an answer of 0, that means that those numbers that you added were opposites. And again, if we start with that positive 5 and you multiply by -1, you get -5, which is the opposite of positive 5. Simplifying algebraic expressions, or just, expressions in general, even though these are all algebraic, they have variables in them. So we're going to take this 3 times 7x, and if you're really strong in your algebra skills, you probably already know the answers. But if you're using these new rules or these new properties of real numbers that I gave you, you would actually recognize that all of this is being multiplied together, so you can apply the associative property of multiplication to move the parentheses around the 7x, and take them away from, or move them away from the 7x, and regroup the 3 times 7 instead, and do that first. And you really see here now that this is 3 times 7, or 21x, and that is the simplified form of 3 times 7x, done with the associative property of multiplication. Well, here we have 2 plus 5x plus 10, and this expression has a couple of like terms that we can add together. Indeed, those like terms are the constant, or the regular value, the term here that has no variable in it, just a 2 sitting alone. And then we have another term, and by the way, terms are separated by addition and subtraction, so we have 1, 2, 3 terms here. And the terms that can be added together, the like terms, are 2 and 10. Now, eventually, and maybe even your teacher's doing it right now, they're just circling the 2 and the 10 to show you what like terms can be added together. But if you're just starting to learn, like we are, the properties of real numbers, we need to show that we can, move these numbers around, the addition signs, use the commutative property of addition, and write 2 plus 10 plus 5x. And now that we have the constant of 2 and the constant of 10, and I'm saying that because they don't have a variable in them, these like terms can be added together now that they're right next to each other, and positive 2 plus positive 10, or just 2 plus 10, is equal to 12 plus 5x. And then down here, this is, we'll use a little bit of property, but it kind of might just seem like I'm simplifying here. I got 42ab, or 42 times a times b, anytime a number and letter, or letters, variables, are touching, that's multiplication. So we have 42 times a times b, divided by, fraction bars division, 6 times a. Well, I can simplify this and help the process along by, writing every sort of similar item with its own fraction. So these numbers, well, 42 divided by 6 times A divided by A, and then I need to show that the B is over something. Well, remember that all of this is being multiplied together, and I want to show a numerator and denominator. So what will I show as a denominator? To have something there, but yet when I multiply, it doesn't change the value of 6a, the original denominator. Well, I'm going to put a denominator of 1 and use that basically sort of that multiplication slash, in this case I can say, kind of like we have an identity really of multiplication. Multiplying by 1 gives us the same answer. And really, you can kind of think that there's a division property, which is, well, if you divide by 1, nothing changes. So we can say now that this 42 over 6 is equal to 7. We have anything divided by itself. Like, what's 2 divided by 2? Well, 2 goes into itself 2 once. 3 divided by 3. 3 goes into itself once. 10 divided by 10. Anything divided by itself is equal to 1. So I'm just simplifying here, and we get a divided by a, which is equal to 1. So 7 times 1. And then b divided by 1. Well, anything divided by 1, just like when we're multiplying by 1, doesn't change the answer. So we just simply have b, and our final answer is 7b. I'm going to step out here and write in the properties that I used a little bit to simplify these expressions, and then we'll be moving on to our last, I think it's going to be our last screen of notes, board of notes. Our previous 3 examples I just worked through, showing them by step and doing the associative property, the commutative property, and writing a little bit down there where I was going along. Those are done with deductive reasoning, which is the process of reasoning logically from given facts to a conclusion. It's one of the greatest things about that you should be learning from algebra is this idea of deductive reasoning, being given a complex situation, understanding that there's a set of rules that need to be followed, and then following those in a specific order so that you logically get from the beginning of your problem to a solution. And then, of course, if you go through more and more mathematics, you'll start seeing some good real-life applications of some of this mathematics. But one of the most important things we're teaching you in algebra is this idea of logically working your way through some complex problems. And then you can apply those logic skills you build in other situations, even outside of math. Counterexample, I've already talked about this. You need only one counterexample to prove a mathematical statement wrong. I've done written down this commutative property of subtraction one more time, but actually drew the number lines for you so you can see the movement as opposed to just my hand moving around. To validate that no, 2 is not equal to negative 2, which is what we get from attempting to reverse the order of 7 minus 5 to become 5 minus 7, or that a minus b, any number minus another number, is equal to that same second number minus the first. Just doesn't work. Okay, so we only have the commutative property of addition and multiplication. Our example here looks very complex, and I certainly would not want to work this out by hand. 5 to the 9th minus 7 to the 4th. 5 to the 9th is a very, very large number. But thankfully, I don't need a calculator to evaluate this expression if I understand, again, that multiplication rule of 0, that anything multiplied by 0 is itself equal to 0. Well, that's what 6 minus 6 is. So we have 5 to the 9th power minus 7 to the 4th times 0. And as soon as one of my factors, that's a long string of basically multiplication, pieces that are being multiplied together, once one of my factors is equal to 0, I know the entire expression is going to be 0, and I'm done. A box of chalk holds 12 pieces of chalk. Just happen to have one right here. Actually, quite a few of them, you can imagine. And a sleeve of chalk holds 9 boxes, and a case of chalk holds 10 sleeves. Honestly, I made those numbers up, but I just wanted to give you a word problem that we'd have to think through and decide, what is the best approach of solving it. And so, this box of chalk holds 12, this box of chalk holds 12, this box of chalk holds 12, and, as I continue that addition, saying that, because ultimately, I have 12 pieces in a box. Now I want to do something about the fact that there's 9 of those boxes. Well, I can add 12 every time I put a new box down, or I can simply multiply by 9. Repeated addition is multiplication. And in the end, I want to know how many pieces of chalk I would have if I were to buy an entire case and these numbers were accurate. besides the fact that 12 pieces are in a box of chalk. So one box is 12 pieces. Okay, well a sleeve is 9 of those boxes, each one containing 12. So it's going to be 12 times 9. And then, okay, and we get an answer from that, which we'll do in a second. But then we have a case which holds 9 of those sleeves. Or excuse me, not 9, but a case which holds 10 of those sleeves. So we're going to do that 12 pieces of chalk in a single box times 9 for the sleeve, and then there's 10 of those sleeves in one case of chalk. So we're going to multiply that by 10. And we got here that we have 9 times, that's the tens place, so 9 times 10 is 90, and 9 times 2 is 18, so that's 90 and 18 is 108. And basically, I'm really just following the order of operations, working my multiplication from left to right, or you can think of me as wrapping that 12 times 9 in a set of parentheses and associating those first two together. And this is all just multiplication, so I can basically multiply any pair of numbers I like, reassociate those groups, associative property of multiplication. So we have, again, 12 times 9 is 108, times 10 is going to be 1,080 pieces of chalk. So let's see here. Kind of running out of room, but when you do a word problem, it's always a good habit to summarize, what does that number actually mean? As we get into solving word problems, and you yourself in your algebra class, a lot of times I'll have students, it's always difficult to set up word problems, but then sometimes I get students that set them up correctly, work out the algebra required to solve those equations or simplify the expressions or whatever, and then they get a number at the end and they don't know what it stands for. So we are looking for, and I ran out of room actually, but we are looking for the number of pieces or the pieces of chalk that are not in just a box, not in a sleeve, but in an entire case that holds 10 of those sleeves. And so 12 in a box times the 9 boxes that are in a sleeve times the 10 sleeves, which we said were in one case. So, I'm Mr. True. Bam! Go do your homework.